Hey everybody, let's take a look today at L'Hopital's rule. You may or may not have had some experience with this already. If you have, we're going to be taking a look at a couple of other different forms of this, but otherwise we're going to take a look at it for the first time for some of you. So L'Hopital is credited with this rule, although Johann Bernoulli was his teacher. His teacher was working with him, and as always, whoever typically published first got the credit. So really, L'Hopital's got credit for maybe some of Bernoulli's work. That happened all the time in early mathematics. So, and here's a picture of Bernoulli. So let's take a look at a situation. Let's consider this limit. So if I go to evaluate this limit, first thing we always try to do is substitute the value in. And if you substitute it in, you can see you're getting 0 over 0, which hopefully remember from pre-calculus means that there is a hole. And do limits exist at holes? Yes, because holes are considered a removable discontinuity. So I could remove that hole. But the problem is that it's 0 over 0 is an indeterminate form. We cannot determine the value of 0 over 0. Which we'll talk more about here coming up shortly. So in this case, we can try to factor and cancel. That's one of our old methods, and these seem pretty approachable in order to do that. In fact, what we're doing is factoring out the whole from your work with rational functions, graphs of rational functions last year, cancel them out. And you get the nice line linear function x plus 2, and the limit as x approaches 2 clearly is 4. Easy enough if you can factor it. But otherwise, we're going to use L'Hopital's rule that says if you get 0 over 0 or infinity over infinity, you can take the derivative of the numerator and the derivative of the denominator separately. This is not a quotient rule. So I'm going to differentiate the numerator and the denominator and then evaluate the limit again. Notice I'm repeating this limit notation every single time. And there you go. 2 times 2 gives you the 4. So L'Hopital sometimes comes in really handy if you really want to avoid any of that fraction work. So L'Hopital says if you get a limit of a rational function where that is indeterminate, 0 over 0, infinity over infinity, positives or negatives, then you can simply take the derivative of the numerator and the derivative of the denominator and reevaluate the limit, which might take a couple steps, but there is L'Hopital's rule. If this is new to you, make sure we're jotting this down either on a foldable or in your notes. And again, as always, you can pause me as we're going through, especially when we're going to get to a couple examples coming up. I might go a little faster than you are, so hit that pause button. Okay, quick little, don't need to jot this down, but a quick little definition or a proof of L'Hopital's rule. So if I take, and I'm going to work it backwards, there's a whole bunch of proofs of L'Hopital's rule. But here, if I take the derivative divided by the derivative, well, here's my old-fashioned, one of my old-fashioned limit definitions, or derivative definitions. Slope of the secant lines approaching the slope of the tangent lines. But I can combine them together into one giant limit. And obviously, I have fractions within fractions. Those x minus a's will cancel out. And in this case, for this to happen, remember the function at a and the function at g would have to be equal to 0. This would have to be indeterminate in order for this to work. So both of those values would have been 0, and there I get back the original limit. So the limit of the ratio of the two functions, assuming that the limit for each individual term was going to 0 and 0. So let's get into an example. Let's take a look at one. So we start out by giving a limit. And then again, the first thing that you always want to do is try to substitute in, see if the function even has a value at that point. Just because it has a value doesn't mean that it's its limit, but it's at least a good starting point. And if you check 1 minus cosine of 0, that's 1 minus 1 is 0 over 0. So there's 1 L'Hopital, take the derivative. Make sure that you are including that limit notation each time. And again, it might be a good idea just at some point just to write that in this case I'm getting 0 over 0 before I go any further. And now when I go to evaluate, the sine of 0 is 0, but the denominator as limit as x approaches 0 is 1, and 0 over 1 gives me 0. So now it's not indeterminate, and I have evaluated the limit, and I'm done. But if you accidentally just kept getting L'Hopital happy and just kept going and going and going. The next step after this would have been cosine over 2 after I differentiate. And the cosine of 0 is 1, and you get a half, and that is just not right. The limit in the end should have been 0. So just make sure every single step you're checking to see, is it still indeterminate or not, before you go on to the next step. All right, again, sometimes we might need to do it a couple times. Let's try this one. If you want to pause me now and maybe try this on your own, first figure out, is it indeterminate? And if so, do L'Hopital. And if it needs to do L'Hopital again, do it again. So if I substitute in 0, hopefully you can see we're getting 0 over 0. So definitely L'Hopital. So derivative, everything here, little chain rule. Oh, I haven't differentiated yet, sorry. And now I'll use the chain rule here. And if I substitute in 0, I think I'm still going to get 0 over 0. And you can kind of almost see in predicting, look at that denominator. It started out as quadratic, then it went to linear. So, and that was causing me the problem, that 0 in the denominator. Well, both places really. But I know I'm only going to have to go one more step. Here is another chain rule. This is not 0 over 0 because of the denominator now being 2. So if I go to evaluate, put 0 into the numerator, into x, I wind up getting negative 1/8. So here is, again, we use L'Hopital a lot when determining convergence and divergence of those sequences we talked about recently. So here is a method to do that, nice and easily, no factoring involved. So now there's other indeterminate forms besides 0 over 0. There are 7 of them that we're going to take a look at. And we'll talk about later why some of them are indeterminate. That's coming up soon. But for now, all of these cannot be determined. If you have infinity divided by infinity, I cannot say it's 1. Remember, infinity is not a number on the number line. It's more of a conceptual idea of a very, very large number. As soon as you pick the biggest number possible, I can add one more and get an even bigger number. So that's indeterminate. I can't determine what that value is. 0 times infinity is also indeterminate. Infinity minus infinity is indeterminate. That is not 0. 1 to the infinity, that's a strange one to think about, and we'll talk about that another day here. That's indeterminate, as well as 0 to the 0 and infinity to the 0. Now the 7th one is the 0 over 0, the one that I started out with. There's your 7 indeterminate forms. You might want to jot those down. Okay, and we're going to have to look at ways of evaluating when I get limits that are in all of these indeterminate forms. In the end, they're all going to be brought back to either as infinity over infinity or 0 over 0 form. So these 3, we're going to work as a common method. This, we're going to work as a common method, and this one as well. There's going to be our kind of 3 variations that in the end, we're going to turn all 3 of those different types back into either a 0 over 0 infinity or infinity. So I can simply use L'Hopital's rule. So here's a quick little chart of my indeterminate forms on the left. The determinate forms, the forms that have a value, are over there on the right. You can pause me here if you want to take a look at that and try to digest some of that. And again, we'll talk about a little bit more in the next days to come about the difference between undefined versus indeterminate. Those are 2 different concepts in mathematics. These indeterminate forms on the left, there we can use L'Hopital. Let's jump in to see these other variations. Okay, so I have a limit. As x approaches infinity, you want to do all of these examples with me in your notes so you have them. Pause me when you need to. So if I substitute infinity, I get infinity times, well, 1 divided by infinity, that's 0. 1 divided by a really big number approaches 0. Remember, talking limits here. And the sign is 0 is 0. So I think I'm getting 0 or infinity times 0. And that's an indeterminate form. So what I'll have to do is I'm going to reciprocate the x term as 1 over x in the denominator. This is a algebraically equivalent expression. And now I'm going to evaluate now. Now the limit as x approaches infinity up in the numerator, 1 divided by infinity, well, that's going to be 0, sine of 0, 0. And 1 divided by infinity in the denominator, that's 0, it's 0 over 0. So that's awesome. That's great. Now, some of you might remember this one limit, that the limit as x approaches 0 of sine of x over x is equal to 1. you remember that graph, it looks something like this. So in it, as x approaches 0, had a limit of 1. And I have 1 over x and 1 over x. They're the same values. We could call that x. It doesn't matter that it's 1 over x. So I think the overall limit is going to wind up being 1, but I don't know. Let's check to be sure. So if I have the limit as x approaches infinity here, so that was 0 over 0, so I have to do a derivative of the numerator and the derivative of the denominator. Notice up in the numerator, there is a chain rule. So derivative of sine of u is cosine of u du. And in the denominator, derivative of 1 over x, the way we do that is we rewrite it as x to the negative first, and then we'll just use a simple power rule on it. And at this point, once I get this expression, those two cancel out, and I get this. And again, 1 divided by infinity, 1 divided by something really big approaches something really small like 0, and the cosine of 0 is 1. So I get 1. All right, so that was the first. This first example is if you get 0 times infinity, you want to just reciprocate one of the terms to turn it into a fraction, and that'll either be 0 over 0 or infinity over infinity, depending upon which one you moved. All right, scenario number 2, this infinity minus infinity, if you check this as you're copying down, the ln of 1 is 0, and 1 divided by 0, 1 divided by something really, really small becomes really, really, really large. So 1 divided by 0 is really, really large. That's your little glimpse into why we call that indeterminate. 1 divided by 0 is so big we can't determine how big it is because it's approaching infinity. So that's a difference between indeterminate and undefined. Or I should say undefined. I guess I said that backwards. All right. So in this case, then I get another 1 over 0, and that is going to be approaching infinity. So what do we do with these? Well, we get a common denominator. And here's my common denominator. Just multiply the two together, which means this first fraction's got to multiply by an x minus 1 over x minus 1 to get that common denominator. And the second fraction has to multiply by an ln of x in the numerator and an ln of x in the denominator. And so that's how I wind up getting my numerator. And then I go in, substitute 1's in. 1 minus 1 is 0, ln of 1 is 0, 0. I think I have 0 over 0. Awesome. So now it's just a matter of L'Hopital. So now when I do L'Hopital, be careful, numerator is pretty straightforward, but the denominator, that's a product rule. So be careful there. You got to do a product rule with that one. And evaluating 1 again. So substituting 1, 1 minus 1. So, and if I do that, now let's see, I get 1 minus 1, that's going to be 0. And 1 minus 1 over 1, that's going to be 0. ln of 1 is 0. That's still 0 over 0. So what I'm going to do is maybe clean this up first. So I've got fractions within fractions. So let's maybe multiply the numerator by x, and we'll multiply the denominator by x. Maybe just a little simplification first here. And if I do that, I'm still going to get 0 over 0 if you check it out. But I like what I see in the numerator now, because one more derivative and I'm going to get rid of that x up in the numerator. So there we go. One more L'Hopital. Again, every single step, I'm rewriting that limit. I haven't evaluated the limit yet. And the ln of 1 is 0. And so substituting in, and I get a half. All right, so the key for this second scenario is that if you get infinity minus infinity, you want to get a common denominator. Easy, easy. All right, now the last forms, these exponential forms. All of these can be using the same method, and we're going to use a little trick with logarithms. So we're going to change these into logarithmic expressions. Just remember that one of our log laws is if you have the exponent, you can bring the exponent out in front. You can move that out in front. That's going to be our key to evaluating these. So one thing, when I do bring it out in front, then I will be able to also then take that n value and divide it by 1 over n. And you'll see why here in a second. So you might want to pause me so you can jot that little equivalence down. All right, so we're going to take, I've got an expression, And this f of x is probably going to be in one of these forms, these exponential forms. But what I can do is I can introduce e to the ln of this limit. Remember, those are inverses. They cancel each other out. So I can do that. And then it doesn't matter if I take the natural log or the limit and then the natural log, or the natural log then the limit, doesn't matter. So I'm going to then change and take the limit afterwards. Oops, let me go back here. And that's going to be my little expression that we're going to want to convert these into. All right, that's really important. Make sure you've got this expression down. So let's do one. All right, so limit as x approaches infinity of x to the 1 over x. So let's just check it here. We've got infinity in the base, 1 divided by infinity, that's 0. Up in the exponent, so definitely one of our forms here. So I'm going to rewrite it into that form we just talked about. E to the limit of x approaches infinity of the ln of x to the 1 over x. So now the problem, I've just moved the problem up into the exponent now, but remember our log laws, I can take this term right here and bring it out in front of here. Now if I go to evaluate this right now, oops, let me just check this out. 1 divided by infinity, well, 1 divided by infinity, that's 0. And the natural log of infinity, remember the natural log function looks something like this. It'll head towards infinity. It doesn't head there very quickly, but it heads towards infinity. So that is yet another indeterminate form. We first started out with the exponential one. Now we've got the 0 times 1. But remember what we can do to fix that? We can just reciprocate one of those terms, or just rewrite the expression as ln of x over x. You can see that of what I have on the slide there. Double checking now. L of infinity, well, that's infinity over as x approaches infinity, infinity. Looks like I got infinity over infinity. So we're good to go. I think I only take one L'Hopital to do that. And then so evaluate that limit. So 1 divided by infinity heads towards 0. And e to the 0 is 1. Don't forget the e, that base. A lot of times people forget that base. So there's that third example. So it's changing it to that other form, that e in the limit ln form we saw over here. And then just going through and just checking to see if I get these indeterminate forms. Ultimately, everything's trying to get it to infinity over infinity or 0 over 0. So now let's go and practice some of these problems so we can see some of the differences.